Well, good morning, everybody. First, I want to thank Aaron, and I want to thank the Linux Foundation for organizing this event. I've spoken at every one of them, and it's a pleasure to be back here and see the momentum grow every single time I come back. I keep thinking it's the year of confidential computing breakout. I've been predicting that for a while. Eventually, I'm going to get it right, and this year might be the year that I get it right. So I'm not going to talk to you so much about confidential AI because there's going to be lots of speakers here talking about confidential AI. Instead, I'm going to talk about something a little bit different, which is based on the trajectory that we've been on at Microsoft for 10 years that we've been working on confidential computing. You can see the portfolio of products and services that we've introduced over that time. The list continues to grow, and it starts from hardware to services, fundamental infrastructure services, up into delivered services for our customers. We're definitely seeing a demand for sovereignty. We're seeing a demand for no boundary confidential computing. Confidential computing for every service is what we've been working towards. But last year, I introduced a way to talk about confidential computing and the promises that people expect and are looking for from confidential computing. Because when you talk about confidential computing, of course, at its core, it means protecting data while it's in use in hardware-based enclaves with attestation. But the workloads, how they take advantage of those enclaves, determines what kind of promises you can get out of those workloads. And so last year, I introduced this taxonomy that we started using internally at Microsoft as a way to kind of frame what are we doing, starting with on-confidential computing, in confidential computing, and transparent confidential computing. I'm going to talk a little bit about each one of these and give some examples of each one. But I'm back here this year after us working for a few years on what's next, how can we extend even these promises? And I'm going to talk about something we're calling confidential tenancy, which really is providing people the sovereignty that they really desire, the complete control over their data, not just the protection of their data. So let's start by talking about what on-confidential computing is. And this is a very powerful tool. This is, I think, what is going to enable the breakout of confidential computing is make it so that there's no reason not to run in an enclave. Because up to now, there's always been some cost to running in an enclave. Whether it's actual dollar cost to putting it in an enclave, whether it's a performance cost to putting it in an enclave, whether it's a complexity cost to putting it in an enclave. But we're at the cusp of all of those disappearing, no matter what the workload, whether it's AI or whether it's standard compute, whether it's a database, putting it in an enclave over this next year, those costs will eventually or essentially disappear. The performance will be on par with general purpose computing, including with communications between CPUs and GPUs, the AI accelerators, that with introduction of protocols like TDISP for attestation, mutual attestation of those devices and encryption of those communications, which has been lacking up to now, are showing up in the market. But on confidential computing, when it becomes easy enough to adopt, now everybody gets some defense in depth. Just toss your workload into an enclave, and now you're protected from the surrounding infrastructure. And you might get some additional protection from data leakage and exploits from outside. And hopefully we're at the point where it's just, why not do this? But to really take advantage of what confidential computing and protecting that data in use gives you, you need to be in confidential computing, which means you've taken the workload and you've actually architected it to ensure that the clear text never leaves a hardware protected boundary. This is something that we're calling the confidential trust boundary. The confidential trust boundary is the protection with hardware and attestations of the data and the code that has access to that data. And this is a little bit different than the trusted computing base of a system. The trusted computing base are those core components that the whole system is built on top of that can't fail to provide security. This is a little bit different. This is saying the data can flow anywhere inside this boundary and it's protected with mutual attestations and hardware such that I can extend it over arbitrary trusted execution environments. And the TCB of that system can be internal to that particular system. So CTB is a little bit broader, is the way we've been thinking about it. And in confidential computing means that you've actually put the components inside of the TCB. All the data runs inside of the CTB. We've also been thinking what constitutes the root of trust of a CTB. And it's really these components right here: the trusted execution environment, the TEE, the attestation services, and the secret manager, where the TEE provides evidence of what's running, what hardware is protecting it. The attestation service examines that, verifies it according to some policy, and releases an attestation token that the TEE, the workload, can present then to a secret manager to get access to a key to then go decrypt that data. These three components are the core root of trust for a CTB. And so with those kind of fundamentals in place, we can think about what is in confidential computing. And in confidential computing means I've designed the system based on this core root of trust, these components, and I keep all of the data within TEEs protected in this way. So we've been on a journey to move lots of critical services at Microsoft into confidential computing. And we're doing this to protect our own data and our own workloads, as well as to protect the data and workloads of our customers. And I'm not going to be comprehensive about all the examples, I'm just going to give you a few highlights so you get a flavor of what we're doing with in confidential computing and what in confidential computing means and how it's valuable to us at Microsoft. But one of the examples of in confidential computing is a direction that we set a few years ago when we were attacked by nation states that were able to get signing keys out of our consumer signing service, Microsoft Accounts, and then use that to get access to customer emails. We decided at that point the root keys are in HSMs, but the keys and the token signing itself is inside of a TE. And so we moved our Entra token signing services and our Microsoft Account token signing services over the last few years to be completely 100% across all regions around the world inside of a TEE. And this is a big step towards us protecting those signing keys. But we've also been taking a look at migrating services that our teams responsible for those services were running in what we call high security environments, which were outside of Azure's cloud, in effectively on-premises data centers with their own networks, their own Active Directory domains, their own administrators, and their own basically flow of software and hardware into and out of it to protect this incredibly sensitive workload and data from attackers that would have a lot to gain by penetrating them. One example is our payment services, where credit card transactions are processed. Now, one of the challenges that those teams all faced with these high security environments is the complexity of them, the capacity limitations, the costs overhead of them, having to buy, for example, new HSMs, and as the service kept expanding, keep on procuring them. And so a few years ago, the payment services team started a migration, re-architecting the payment services to run inside of Azure Confidential Computing with the goal of achieving the exact same promises that they were able to get in their high security environment, but in a commercial cloud, Azure, using confidential computing. And so you can see here a simplified architectural diagram of that payment service and how it protects the credit card numbers from workloads and exfiltration, translating them into tokens based off of signing keys, decryption keys that are used to encrypt and decrypt them that are in HSMs. We've also been migrating other sensitive services that are incredibly valuable to Microsoft, like our licensing key services. And about a year ago, shortly after the last CC Summit, we finished a migration that we'd started of migrating Windows licensing keys into confidential computing in Azure. Again, another service that was in one of these high security environment on premises, completely migrated to Azure. And then, exciting to a lot of people that play games, we migrated our Xbox token signings or Xbox licensing service, which is called XKMS, into Azure. So anytime you're playing an Xbox game, you're interacting with a confidential computing service that is architected to be inside of confidential computing. And it doesn't stop there. Our full Microsoft signing services also completely inside of confidential computing. And then just recently, to help our customers with this pain of passkeys and having passkeys bound to a particular hardware device, breaking free from an individual device, how could we do that securely? We don't want these passkeys to be flowing out in the clear and then be leaked, compromised, and then be used from other devices that are not authorized by that user. So our Edge team looked at this problem, saw confidential computing as a way to actually protect the keys end to end from one device to another, allowing a user to roam their passkeys. And that architecture is now up and running, allowing our users to roam passkeys between devices by leveraging a cloud-based confidential container which manages the encryption and decryption of those keys and migration between users' devices. So another great example of something that prior to confidential computing, without confidential computing, we probably wouldn't feel comfortable doing this, given the enormous risk of having these keys floating around. And then one more, multi-party computation. I've been talking from the start here about the value of multi-party computation with confidential computing, which doesn't have the performance overheads and complexities of fully homomorphic encryption, secure multi-party computations, but actually lets you run at native hardware speed, fully compatible with all software, and then allow multiple parties to collaborate with rules around who gets access to the data that's being shared. And maybe nobody gets access to anybody else's data. They only get access to the results. And maybe even then, only one or a few of the parties get access to the results. That's made possible with these confidential clean rooms. And we've got confidential clean rooms now with Spark Analytics in preview, which allow customers to come and perform analytics together, with the parties agreeing on contracts basically for what software is allowed to access the data, and then based off of attestations of the configuration and the code, releasing keys to the computation that then only allow those particular queries to operate over it, and only the specific parties to get access to the results of those queries. So this is something we're seeing a tremendous amount of interest in. You can imagine all the scenarios, from governments that have different departments that aren't allowed to share data with each other, to healthcare, where you've got different parties with different data sets, again, can't or unwilling to share data with each other, but want to get joint insights out of it, and the list goes on and on. And then the next phase, though, of confidential computing, the next step up, is something we call transparent confidential computing. So it builds on in, but it brings something else into the picture, which we recognized when we were talking to customers about not just being IaaS-based when they talked about moving data into confidential computing, not just saying, I've got control over all the code. But if you've got control over all the code, you're not able to take advantage of cloud services. How can we give customers the confidence to let our services enter the CTB with their data? One way we can do that is with confidential computing, to give them guaranteed auditability of the code and configuration that touch their data at any point in time. And we do this in a way that we describe in this Communications to the ACM article we published a couple years ago, a self-sustaining system that will preserve this guaranteed auditability property even as it's upgrading itself, without users having to go manually approve every code update. This is all based on something that we call a Microsoft Signing Transparency Service, because what you have is a service that basically will only sign software, only sign artifacts, if it adheres to a certain policy. And it stores this fact that it signed it in an immutable ledger, and it returns a receipt that goes along with the signature that allows somebody to prove this thing actually adhered to some policy. And the relying parties for this can include the code itself. I'm only going to upgrade myself if it's in the ledger, and the policy that allowed it to be signed and put in the ledger says, A, the code is escrowed out of the party's control, and B, it was reproducibly built or had an attested build. And with those two properties, you guarantee that an auditor comes along, they can get access to the original code that went into that component, that service, and they can verify that it is actually what ran and had access to their data. Again, fulfilling that guaranteed auditability property of transparency. So Microsoft Transparency Service, we've just released it literally recently, and the way that it would work is you have a signing pipeline with something like Microsoft Artifact Signing. Ideally, a confidential builds pipeline. So you don't need reproducibility, but you need measurements and attestability of what went into the build. Then you sign the code. And this signing of the code at this point is just, hey, it's Microsoft code. It came out of a particular pipeline. But the transparency service then looks at a policy, again, a policy like the one I just gave you an example of. And if it meets the policy, records in the ledger, returns a receipt. And then that receipt can be leveraged by confidential services to gain trust in this thing. It can also be leveraged by a customer to gain trust in this thing, and through an auditor that can go and say, I need to look at the code. And instead of, hey, this is the code right here, they get cryptographic proof that that code is the code that has access to the data or had access to the data at a particular point in time. So this is our step on this journey towards transparency, and we're already building a number of our core root of trust, the CTB services, which are the most fundamental to confidential computing, in this transparent way. But I'm excited to talk about our vision to take this a step further, because one of the goals from the start with confidential computing and our thinking about it has been, how do we take, if possible, not that it would necessarily always be the case, but take Microsoft out of the CTB to get altogether. And so the way that we're thinking about that is mapping effectively what an air-gapped cloud looks like into a commercial cloud. In an air-gapped cloud, you've got an environment, and it's got something called a data diode. That data diode controls all the data that can go into and out of the environment, and it is the mitigation for a compromised piece of software getting into that environment because it cannot exfiltrate data. And this is the way that all nation states protect their most sensitive secrets, is with this diode, which has policy enforced for what can come out. We're implementing right now, designing and implementing a virtual data diode based on confidential computing that gives a customer complete control with their policies of what data comes out of a service provided by Microsoft. The data diode effectively is their boundary around our service, so that even if we get compromised or we put in a backdoor, the data can't come out because their policy blocks it. And they've got complete control over what goes in and out. And with this kind of fundamental building block, we can get to that sovereignty that Jim was talking about, where somebody can create basically an air-gapped data center that isn't just in one location like it is today on-prem, but actually spans multiple cloud regions, because they've got full control over the data that comes out of that environment. They've got full control over the data that goes in, and this boundary, then it can extend and create a bubble, basically an air-gapped environment that spans multiple regions, giving them not just the data sovereignty that Jim's talking about, the digital sovereignty, but also resiliency. Because now, if they're being attacked as a nation state, their air-gapped environment isn't sitting here in a data center that somebody can point to, but is actually in the cloud and able to move around. So this is our next step on the journey that we've got, is this vision going from on confidential computing, let's just make this the default, in confidential computing, designing with tools that are becoming easier and easier to use, workloads that protect their data all the time with TEs, to transparency, they'll be able to guaranteed audit what happened, when, and finally, confidential tenancy to really fulfill that digital sovereignty vision with cryptographic guarantees over what controls are accessible to that data. This is the vision that we're on, and this is what we hope to continue. It's an exciting year for confidential computing, and I want to thank you very much again for inviting me to come up here and speak.